Well, first I'd like to thank the organizers for organizing this lovely conference and inviting me to speak and giving us the opportunity to honor Bill. Now, I know Bill looks much, much older than me, but that's just his dissolute lifestyle. It'll come as a shock to most of you to learn we're actually the same age and have known each other since we both entered the business. And many years ago, I realized that how much I enjoy a conference depends to a large extent on whether or not Bill is there. And this is for several reasons. Not only does he give great talks, but he's also enthusiastic about other people's mathematics, and he's fun to be around and is a cheerleader and a good example for the whole field. And I think he's a major reason why our field is a supportive and enjoyable place to work in. So thank you, Bill, for all you've done for mathematics and all you've done for us. What I want to talk about today is joint work with Alexander Aleman, Michael Hartz, and Stefan Richter. But before I tell you about what we did, first I need to go back into prehistory. That's the 1980s. And if what I talk about sounds weird, remember this was before TikTok. So to amuse ourselves, we had to work on strange mathematical problems instead. So let me start with the Smirnov class. So the Smirnov class is the largest class of holomorphic functions on the unit disk for which an inner-outer factoring makes sense. Now, everything you need to know about inner-outer factoring was on slide 1 of Professor Havenson's talk yesterday morning. But let me just remind you that an outer function, by definition, an outer function is a holomorphic function with no zeros on the unit disk, whose logarithm you can represent as the Herglotz integral of the logarithm of its modulus on the boundary. So in order for that to make sense, you're integrating against the logarithm of the modulus. The logarithm of the modulus has to be integrable. And that's the only condition to be in the Smirnov class. So let me define it. N plus, well, there's a couple of ways to define it. You can define it intrinsically. Let me do that first. It looks a little weird. It's the set of, oops, we're sliding. It's a set of holomorphic functions such that the sup of the integral of log of 1 plus the modulus of fr d theta, where r is between 0 and 1, is finite. So f sub r of e to the I theta is f of r e to the I theta. And it's not quite this. It's this plus an extra condition. And the limit as r tends to 1 of the integral of log of 1 plus f minus fr d theta is 0. So that's kind of an intrinsic definition of the Smirnov class. This apparently is how you write the first letter of Smirnov's name if you don't have Cyrillic font. You use an N plus. You can also write it as the union of all quotients, where f is in the Hardy space and m is an outer function in H infinity. So I can think of it as a vector space. I can think of it as a union of the vector spaces H2 divided by m over all outer functions m. And there's a standard way of making this into a topological vector space. I put a topology on this, so we'll find a topology I'll put I subscript LC as a locally convex topology where by definition you say a basis is given by the convex sets with the property that U intersect H2 over M is open for every M. So I topologize H2 over M just by declaring that multiplication by M is unitary between that and regular H2. And so now I have a union of vector spaces, and once I have a union of vector spaces, a union of topological vector spaces, I can make them into a topological vector space in their own right just by this inductive limit construction. And Henry Hellson was very interested in the question of what is the dual of this space.
So the point is that they're closed under products, and M's we can get products of them. So they can get bigger and bigger, H2 divided by...
As M gets smaller and smaller, this space gets bigger and bigger, yeah.
So if I take a product, then I get a bigger space.
Yes, yes. I guess I'm wasting board space over here, aren't I? Yeah, exactly. The plus means you aren't dividing by anything with a singular inner part. Okay, so why did Hellson think this question was interesting? Well, suppose gamma is in the dual. That's a very long way up. I can't even see it. Nope. Suppose gamma is in this dual. So gamma will send the function z to the n to some scalar gamma n. And let's form the power series H. H of z is the power series that has these Taylor coefficients. So saying gamma is in the dual of this inductive limit topology is the same as saying that if I apply gamma to, let me keep my letters straight here. Well, it says that gamma is bounded on each individual space. There's no uniformity here. In order for this to be continuous on this inductive limit, it's the same as saying that gamma is a continuous linear function on each space. So if I take gamma of some function g, well, on the one hand, I can expand g in its Taylor series, and I know what happens to each z to the n. So formally, at least, this will be the H2 inner product of g with this function h. Imagine g is just a polynomial if you're worried about convergence. On the other hand, it's supposed to be a continuous linear function on H2 over m, so it should be an inner product in H2 over m of some element of H2 over m by the Riesz representation theorem. And then by definition of my topology here, I just multiply both sides by m and take the inner product in H2. So that's the same as mgf in H2. Well, I can pull this m over here, and this is the same as g in the product m bar f in H2. So now I compare both sides. You can put a projection if you like, but okay. In fact, I want to put a projection in here. Let me leave it as H2, where this is the projection from L2 onto H2. So now you compare both sides, and G is an arbitrary function, and you say its inner product with H has to be its inner product with F multiplied by M bar projected back onto H2. And this has to be, so that's the same as saying that H is in the range of so H is in the range of the Toeplitz operator with symbol M bar, which I can also write as the adjoint of the multiplication operator with symbol M, where M sub M from H2 to H2 is just multiplication by M. So if gamma is in this dual, it's the same as saying this function h here that you build up from what gamma does to z to the n is in the range of every co-analytic Toeplitz operator. And so that was why Helson was interested in this. So this is due to Helson. The dual of the Smirnov class in this topology, you can identify with the intersection over all outer M, let's say M cyclic for the shift, of the range of the Toeplitz operator with symbol M bar, which is the same as the adjoint of the multiplication operator by M. And Helson was interested in understanding what this said about the function h. So let me observe that being in the range of all these co-analytic Toeplitz operators is in some sense a smoothness condition. So if I want h to be in the range of multiplication by 1 minus z, the adjoint of that, you can work this out, and it'll tell you that, well, let's say as I look at 1 minus z bar times sum a n z to the n equals 0 to infinity, and I project that. So what do I get? I get a0 minus a1 plus a1 minus a2z plus a2 minus a3z squared. So being in the range of this particular Toeplitz operator says that your Fourier series has this form. And you notice this is a telescoping Fourier series. If I try and evaluate this at the point 1, it will converge because I get cancellation. And if I change 1 to some other point on the unit circle, I'll get the Fourier series converges there. So being in the range of all of these, if I replace this now by some tau in the unit circle, being in the range of all of these says that H's Fourier series converges everywhere on the unit circle, not just almost everywhere. And if I put a power in here, I can get the same argument for the derivatives. So I get that every derivative has to converge everywhere on the unit circle, so it's a smoothness condition. But exactly what smoothness condition? Well, Helson didn't realize it, but the answer was, he proved this in 1987 and asked the question for an intrinsic characterization. The answer was actually already known in the work of Yanagihara. So in 1973, Yanagihara had also looked at the Smirnov class, but he'd used a different topology on it. So I can define a metric D, no, let me call it rho. Rho of Fg is the sup of the integral of log of 1 plus fr minus gr d theta. This gives you a metric that makes the Smirnov class into a topological vector space with a complete translation invariant metric. And you've calculated this dual. And the condition is gamma n has to be less than or equal to some constant times e to the minus c, the square root of n, for some constants m and c. Now, Helson didn't think this answered his question because this topology is not locally convex, whereas this one is. So it's a different topology, and so you expect it would have a different dual. But it turns out that it's not that different. So a theorem I proved in 1989 was that I can define a different topology. So I use the structure LC deliberately. If I define a topology just by the non-locally convex topology, I say U is open if and only if U intersect H2 over M is open for every M. Then this topology is exactly the same as the metric topology Janicki-Hauer studied. So obviously this is a finer topology than the one where your basis requires them also to be convex. So you get that maybe I should write this over here. So I get n plus rho embeds into n plus I locally convex. So any linear functional here is automatically a continuous linear functional here. But if I have a continuous linear functional here, since you're mapping into the complex numbers, all you care about is the inverse image of open disks, and those are going to be convex. So the only sets that matter here in deciding whether or not a linear functional is continuous are the convex ones. So since these have the same convex sets, they'll have the same duals. So we get that this is this. And therefore, the answer to Helson's question is that you're in the common range of all co-analytic Toeplitz operators if and only if your Fourier coefficients decay like e to the minus c square root of n. Okay, so that's the prehistory. Well, it's not quite it's most of the prehistory. So then you prove something in the disk, and then you hear Uncle Walter asking in your ear, so you've done it for the disk, what happens on the ball? So a natural question to ask, at least in the late 80s, a natural question to ask was, what happens if I replace the disk by the ball? So what is the intersection of the range of the adjoint of multiplication operators where now I'm thinking of this on the Hardy space of the ball in CD, and then will be a multiplier. Oh, I was a little vague here. Here I wanted my multipliers to be cyclic. It doesn't really matter whether they're cyclic or not, because if I look at, suppose I multiply my outer function n by an inner function I, and I observe that if I multiply the function if by the conjugate analytic function m bar I bar and project, that's the same as if I multiply f by m bar. So the common range will be the same whether or not I allow inner factors. So m in h infinity or m cyclic, you could ask either question. You could ask, what is this on the ball? And there was a theorem analogous to Janágy-Hara's due to Navracki, which characterized the dual of the Smirnov class on the ball. So Navracki in 1989. So I can take that top definition for the Smirnov class of the disk and replace Lebesgue measure on the unit circle by area measure on the unit sphere, and you get the Smirnov class on the ball as described in Rudin's book, for instance. So if I take n plus of the ball and I use the same metric, the dual of that, it's exactly the same as Janágy-Hara's description, except I replace the square root by the power of d over d plus 1. So gamma sends z to the alpha to some gamma alpha, and then gamma alpha has to be less than or equal to some constant e to the minus c alpha to the power of d over d plus 1. So this looked promising, that maybe you could follow the same argument here, but this turns out this is not equal to this common range. Which was a mixed blessing, because it didn't answer the question, but knowing it wasn't equal to the common range enabled Boris Korenblum and me to answer a question of Rudin's. So Rudin had asked another question. Suppose W is a non-negative function on the boundary of the unit ball. Let's say for convenience it's continuous. Rudin didn't actually require that. And log integrable. So Rudin asked, is it the modulus of an h infinity function? And by a complicated construction, we were able to show that knowing the answer to this, that these two things were different, meant the answer to Rudin's question was no. Now, once we published this paper, Herb Alexander said, well, you really don't need operator theory to prove this, do you? And he sat down and he came up with a much simpler construction that didn't use operator theory. But it's a psychological fact that it's easier to prove something if you know it's true. So I still consider this a contribution of operator theory to several complex variables, even if the several complex variable community have erased the operator theory from the history. Okay, I'm done with the prehistory. So now let me tell you about the more recently. Well, now we're in a brave new world. We have all sorts of modern tools. We have Bitcoin, and we have the Drury-Arveson space. So we can so H2D, this is the Drury-Arveson space. On the unit ball, best described by the kernel, the reproducing kernel, is 1 over 1 minus z inner product w on the unit ball. And one can form some version of the Smirnov class by looking at the union over cyclic multipliers m of h2d divided by m. We can look at this as before, and we can make this into a topological vector space as before by putting on the locally convex inductive limit topology, and then we can ask what its dual is. And exactly the same argument I have up there for, where did I put it? Up here, for Helson's argument, you get exactly the same conclusion that you can represent the dual as it's the set of H, such that H is in the range of the adjoint of the multiplication operator for every cyclic multiplication operator. And you can ask, is there some intrinsic characterization in terms of the decay of the Fourier coefficients? Well, the Drury-Arveson space, you can think of in a variety of ways, but one way of thinking about it is to observe that if I take any one-dimensional slice through the ball, this gives me exactly the Zago kernel on that disk. So the Drury-Arveson space is in some sense a uniform version of what you get if you take the Hardy space on one disk and then you spin it through the entire ball. So with that in mind, you could define some sort of a uniform Smirnov class to be the set of holomorphic functions on the ball that are in a uniform way in the Smirnov class on every one-dimensional slice. So you want the soup over all zeta in the boundary of the ball of the integral of log of 1 plus f of r e to the I theta zeta d theta. You want that to be finite, and you want the radial functions to converge in norm to the boundary function, where rho of fg is going to be, again, a soup over points in the boundary of the soup over r of the integral of log of 1 plus f minus g evaluated r e to the I theta zeta d theta. So this is saying that you're uniformly in the Smirnov class at every one-dimensional slice you take. And our first theorem we're able to calculate what the dual of this is. So if I take this uniform Smirnov class with this metric, and I calculate its dual, so this will be the set of gamma such that the monomials go to some numbers gamma sub alpha, and the decay on the gamma sub alphas you need is that gamma alpha has less than or equal to some constant times omega alpha, I'll tell you what that is in a minute, times e to the minus c times the square root of the length of alpha, where omega alpha is alpha factorial over the length of alpha factorial. This is the norm of z to the alpha in the Drury-Arveson space. So this means alpha 1 factorial times alpha 2 factorial all the way up to alpha d factorial, and this means alpha 1 plus alpha 2 plus alpha d, that whole thing factorial. Okay, so that seems promising. You go up. And you come down. But then some bad stuff happens. We have two problems. First problem is that the space we care about is a proper subspace now. So when d equals 1, at least as sets they were the same. But now as a set, this is strictly smaller than the space we just characterized the dual of. Well, that's not so bad, but what really is bad is the embedding isn't continuous. So if I put this topology on here, so not only is it a proper subset, but the inclusion is not continuous. So things look pretty grim. We understand the dual of this, but since this inclusion is not continuous, it's not obvious that any linear functional here is necessarily continuous here, and because this is not equal to this set, it's also not clear that any functional here should extend. But then a miracle occurs. And the miracle is an idea that goes back to Yannick Ihara. Oh, I should have said that you might think the natural way to define a topology on a union of spaces is this one here, the one I call the non-locally convex topology. The disadvantage of that, however, is it doesn't necessarily give you a vector space. That if you do it that way, there's no guarantee that addition is continuous. But Yannick Ihara had the idea that certain times when, so this is a space that is complete and has a translation invariant metric, but it's not a fresh A space because it's not locally convex. But he had the idea that maybe there's a smallest fresh A space that contains it. And we were able to mimic that idea and say there is. So this is a fresh A space. If I have time, I'll tell you what it is, but I may not have time. And a couple of good things happen. These have the same dual. And this inclusion is not just continuous. In fact, it's the exact same topology, restricted to this subset. So this is dense and the same topology. Which means we win after all, because since this is continuously contained in here, any linear functional will restrict to a linear functional here, and we know that these have the same dual, but since this is dense, we'll get all of them. So we're finally able to get our main result. The intersection of the range of the adjoints of multiplication operators, where n is a cyclic multiplier for the Drury-Arveson space, is the same as the set of functions where gamma alphas satisfy this decay condition. And let me just finish with two open questions. We don't know what happens if you replace cyclic by all multipliers. And we don't know the answer to that question up there. What happens if you go from the Drury-Arveson space to the Hardy space? So question 1, what about all multipliers? And question 2, what about the actual Hardy space, not the Drury-Arveson space? I'll follow Chris's example from this morning. I'll offer, I think this one is actually a slightly easier question than this one, because there's kind of a feeling that there's only a polynomial difference between the Hardy space and the Drury-Arveson space, whereas this condition is kind of sub-exponential. So I'll offer a beer for this one, and I'll offer a bottle of wine for this one. Thank you.
If you have a question for John, please wait for me to figure out how to turn this on and then hold the microphone to your mouth. Any questions for our speaker?
I just wanted to know if, does the complete Nevalena peak property of the space play some role in your proof, or it's more an analytic?
It's purely analytic. We don't, correct me if I'm wrong, Michael and Stefan, but I don't think we use a Nevalena peak property anywhere. And our estimate blows up as d goes to infinity. So you can't just say it's automatically going to be true on all. I mean, our estimate may not be sharp, but the one we have does blow up.
Other questions? Let's thank John again.